Hello and welcome to my video about work energy theorem and efficiency. All right, so work energy theorem is essentially that first of all, we'll get the idea of conservation of energy, which I know is in a future video, but energy cannot be created or destroyed, so energy must go somewhere. And so what we say with the work energy theorem is that when you have a change in energy, that is the work, okay? And so what we can talk about here is the change in energy from an initial state to a final state. So usually we're talking mechanical energy. So total mechanical energy at the beginning should equal total mechanical energy at the end, but it doesn't. Why doesn't it? Usually because of friction and heat loss, sometimes because of sound, light, other sources of energy loss, rotational energy, because we're only talking about linear mechanical energy right now. So there are other sources of lost energy, but we're going to say mostly it's friction and it's heat. And that's why we use this delta H for heat. So whatever change in energy, whatever lost energy will go into usually a heat. It goes somewhere. Okay, so let's go ahead and do some examples with this. Example number 1 says, smart cars extremely small, light, and fuel efficient 3-cylinder cars. Determine the amount of work that must be done to accelerate a 790 kilogram smart car. Wow, that is very small. From 10 meters per second to 30 meters per second. So if we're looking for the work done, we need to look at the energy that it took, right? And so what we're just going to say is that work equals, and then we can just say change in energy. And so this is going to be energy final minus initial. Now, the energy final is an EKF, and energy initial is also an EK, but it's an I. So we're going to say that this is mvf squared over 2 minus mvi squared over 2. Okay, so with this done, we can say, well, we can just plug this in our calculator. Actually, before we plug this in our calculator, let me just take out a greatest common factor of mass over 2. Makes my life a little bit easier. It's not significantly different, but it's just going to make it a little bit easier to type into my calculator. And so we're going to have mass, which is 790 over 2. And then we're going to have our V final, so that's 30, minus our V initial, that's 10. And both of those are squared prior to them subtracting. That's an important fact. And so we have 316 kilojoules. 1,000 joules, right? 316,000 joules. Just noticing my sig digs, I'm going to say that this should have 0.0. Okay, so this is a good way to answer the question. It's not the only way to answer the question because you'll notice that the smart car is accelerating, right? So we can use our kinematics formulas to solve for the acceleration here. And if we can find the acceleration, then we can find the force. And if we can find the force, then we can find the work done. Right? So there's actually more than one way to solve this, but let's just go ahead and write this down. Ooh, nope. Unfortunately, this is not going to be possible because we don't know our displacement or our time. So actually, this will not be possible for this question. But maybe if you were given one more piece of information, you could solve it that way. Okay, let's go ahead and try our next example. A 165 gram, not kilogram, that's important later, a hockey puck is sliding at 20 meters per second and slows to a speed of 9 meters per second in a distance of 8.1 meters. Determine the force of friction causing the puck to slow. Okay, so what we can say here is that the puck is going to slow down due to friction. Okay, so we can use, again, the kinematics to find the force of friction. So if we find acceleration, let's see here, VI, VF, that's given. Distance is given, so time is not given. 8.1, 9.0, 20. Okay, and so which formula are we going to use? It's going to be VF squared equals VI squared plus 2AD. Solving for A, we're going to get VF squared minus VI squared over 2D equals A. Okay, so this is a good formula to use, and we can solve for our acceleration here. Okay, and you'll notice that we have a negative acceleration, negative 0.69 meters per second squared. So you'll notice we have an acceleration that's negative. If we're trying to find the force, that's force equals mass times acceleration. In this case, it doesn't actually matter that it's negative, but it's interesting to note. So just make sure you change your mass to kilograms, and we get a force of 3.25 newtons. Now, it is technically a negative, like it's slowing it down. Okay. Now, determine the efficiency of the system if the goal was to slide for as long as possible. Well, what's happening? What does efficiency mean? Efficiency, this is your formula for efficiency. Efficiency is the energy output, or another way of saying that is useful, over the energy input, or used. So how much energy it actually used versus the energy that it put out, and then times by 100%. This formula is not in your formula sheet. This is something that you just kind of have to know. And this idea of energy in versus energy out is very, very important. And yeah, it's basically like calculating a percent on a test, right? We know that we're always going to have less than 100% efficiency, so that's something to keep in mind. So you take the smaller of the energies, you put it on top, and the bigger on the bottom, and you go from there. So in this question, the efficiency of the system, well, in an ideal world, the used energy is actually the energy that it has at the beginning, which is the sliding of the puck, right? So it's the EKI. And then the energy at the out is EKF. It's the final energy. Ideally, according to this question, the goal is to slide for as long as possible. So for them to have the same amount of energy at the end as it has at the beginning. But that's not what's happening here. It is slowing down. So we're losing some of that energy. Ideally, they would be perfectly balanced top and bottom, but they're not. Okay, so what can we do to solve this? Well, we can actually go a half mvf squared over a half mvi squared times 100%. Now, the half will cancel, the mass will cancel, And so we're going to be left with the efficiency equals VF squared over VI squared times 100%. So doing this calculation, it's going to be 9 squared over 20 squared times 100%. This is not changing it to a decimal, so I'm just going to do that here. 20.25%. So just double checking our sig digs here. It should be 20% efficient. And I guess my force should also be in sig digs, negative 3.3 newtons. Oh, you know what? I think it rounded already. I think it was negative 3.249. Yes. All right. So I hope this video helps you better understand the idea of work with the work and energy theorem, as well as the idea of efficiency. I hope the video helped, and good luck.